As you can see, I'm zooming from home. All campuses are closed. So what we're going to cover today is Chapter 3. And the first exam will be on Chapters 1, 2, and 3. Next Thursday, we'll have a review using the review document that I provided for you. And then a week from today, we'll have exam number 1, either in person or in Brightspace. And on that same day, I'll get into Chapter 4. If people show up in class and take the exam in class and need more time, then I've built in a buffer so that I can move Chapter 4 to the following Thursday, and then following Tuesday do Chapter 5. So we're going to finish Chapter 3 today on matter. That was one of the first things they taught us in grade school. What is matter? Very, very simple definition. Matter is anything that occupies space and has mass. We're in this course, we're going to be concerned only with 3 states of matter: solid, liquid, and gas. There are other exotic forms, but they're not very useful for a beginning course. As you may recall, one of the skills that will be helpful in understanding chemistry is to develop sort of an intuition, a connection between what you observe in the macroscopic world and what's going on underneath in the microscopic world. So this is an attempt to give you an idea of why things are the way they are. For a solid has a definite shape and a definite volume. And the reason it has that is at the microscopic level, all of those particles in the solid are locked in place. They don't move around. They may vibrate, but they don't change their position. Whereas a liquid, if we add energy, we can break some of the bonds that are holding those particles together, and now they're free to move past one another, which only changes the volume slightly. And they have a definite volume at any given temperature, but not a definite shape, because their particles are not locked in position. Then if we add more energy, we can convert a liquid to a gas. And all this time, we're talking about one substance. And to keep things simple, we're talking about a pure substance. So we haven't changed the identity of the substance. There's no chemical change occurring. This is purely physical. Once you reach the gas phase, now the particles, the bonds that are holding the particles in close proximity as they were in the solid and the liquid, now those bonds are completely broken. And these particles are free to move as wherever they want. And that means that they don't have a definite shape and they don't have a definite volume. Gases will expand to fill the container. And if you don't have a sealed container, the gas will escape. I'll point out one thing about this model. We're using water as our model here. What you may notice is that between the liquid and the solid, the liquid molecules are closer together. There's a lot of empty space in the solid. That is due to the way that those water molecules lock into their crystalline form. they actually expand in volume by introducing this space in the middle. What that means is that the same mass of ice as the water occupies more space. So that means it's less dense. That's not typical for most solids and liquids. Solids are generally more dense than liquids, and liquids increase in volume slightly, which decreases their density. And of course, gases, they always decrease their density relative to the liquid and the solid. Okay, I mentioned earlier that solids have a rigid, definite shape, and they have a fixed volume also. These are just some examples. Liquids, on the other hand, have a definite volume, but no definite shape. They will have to assume the shape of the container. So those are some examples. Gasoline is a mixture. We're going to talk about that in just a minute. Water is pure. Alcohol is pure. Blood is a mixture. This just illustrates the fact that water, any liquid, will assume the shape of its container. Gases have no fixed volume and no fixed shape. So their container must be sealed in all dimensions. Air is a mixture, mostly nitrogen and oxygen. Helium is a pure substance. Oxygen, when it's delivered from a tank, is pure. Now let's talk about properties. What are properties? They properties are characteristics of a substance. Physical properties are characteristics of the substance that can be changed without changing the identity of the substance. The author here likes to use composition. I think identity is a better word. Identity fixes the kind of substance that you have. And anything that changes a physical property without changing its anything that changes a property without changing its identity is a physical property. For instance, and these properties are observable. These are macroscopic properties, such as odor or color or volume or solid, liquid, or gas. That's a property. Density, melting point, boiling point. Now we're getting into the realm of potential. We're not saying that there's a change that has occurred. We're just saying this is the way it is now. But when we talk about melting point, it has the potential to change from a solid to a liquid at this temperature, or from a liquid to a gas at this temperature. That is a physical property. We're not saying that any change has taken place. It's simply the potential. Chemical properties, on the other hand, identify a substance's ability to change its identity. Now we are definitely talking about potential. So a substance that has the potential to change its identity, that characteristic is a chemical property. For instance, flammability. If we say paper is flammable, or steel can rust, or food that you take into your mouth will has the potential to be digested and supply energy. Those are chemical properties because we are actually changing the identity of the substance. We're speaking to the potential for change. Now, which one of these would be a chemical or physical property? Ethyl alcohol boils at 78 degrees. We're not changing the identity. We're not even speaking of potential for changing. So ethyl alcohol would be a physical property. Hardness of a diamond. That's also a physical property. Sugar fermenting to form ethyl alcohol. Sugar has the potential to form another substance, change its identity. That's a chemical property. Now, when the property, or what we have spoken to as a property, actually changes, that's a physical change. We're actually describing the change of a substance from one form to another without changing its identity. So if we boil or freeze water, that is a change from one state to another. We talked about this already, these three states. It's still water. It's just in a different physical state. And if we say that we're melting ice to form liquid water, we're describing a physical change. The things that usually change in a state are the motions of the molecules. Now we're talking about kinetic energy. Right? And if you've never seen this before, kinetic energy of any object can be quantified by introducing its mass and its velocity into this equation. And you can calculate its kinetic energy. So if we're talking about the same particles, the mass doesn't change. All we're changing is the velocity, which means energy, right? Because we're increasing that means the energy is increasing. And if you're increasing the energy of a substance to make a phase change, that means energy has to be added to the substance in some form or fashion. You can heat it up. Sometimes you can just shine a certain wavelength of light on it. You can add energy to the substance and cause a phase change. Now, chemical change, we are describing an actual change of identity of a substance. So if we say in a Bunsen burner, methane reacts with oxygen to form carbon dioxide and water. So we're changing both methane and oxygen. They no longer exist. Now we have produced carbon dioxide and water. That is a chemical change we have just described. Another example, we can use a direct current through water that has a little bit of acid in it, because water is an insulator. It won't conduct electricity. So we need something in there to help move the electrons and move the charges. And by so doing, we can split the water molecule into, change its identity from water to two different gases, oxygen and hydrogen. That's called a decomposition. This electrolysis of water, electro means is referring to the movement of electrons, electricity, and lysis means to split. So by using electricity, we have split the water molecule, causing it to decompose into two different gases. The most notable difference is at this temperature, water is a liquid and hydrogen and oxygen are gases. So that's one indicator that you've changed the identity of the substance. And the other, another way to tell that you've changed the identity is to test the gases. Right? We have a hydrogen in one side, oxygen in the other side. If you take a glowing splint, right, it's a specially treated piece of wood, and you light it and you blow it out, but it still glows red hot. And you put that in the oxygen side, then the splint will burst into flames. If you put the splint in the hydrogen side, it will pop because oxygen in the air reacts with hydrogen, and all it needs is a little bit of energy to get it going, and it will reform water. If you try to do that with water vapor, nothing happens. Well, the splint goes out. Okay, how many of these following changes describe chemical changes? If we pulverize rock salt, have we changed its identity? No, we just made the particles smaller. So that's not a chemical change. If we say wood is burning in our fireplace, that's a chemical change. We are converting cellulose and lignin primarily into carbon dioxide, water, and ash. And ash is a complex mixture of solid substances. Dissolving sugar in water, that doesn't change the sugar or the water. They're still the same. How do we know? You can recover the sugar and the water. All you have to do is evaporate the water, right? You can boil it, or you can just wait for it to evaporate. You get the sugar back. It never changed. If you want to recover the water, then you have to catch the vapor and condense it. So that's a physical change. Melting a popsicle on a warm summer day is a physical change. All you're doing is changing from a solid to a liquid. So burning wood is the only description of chemical change in this example. So again, if we ferment sugar to ethyl alcohol, we're changing the identity. That's a chemical change. If iron metal is melting, right, in a furnace, say, we're only changing the iron state from solid to liquid. That's a physical change. And iron combines with oxygen to form rust. Rust is a new substance, a different identity. That is a chemical change. Now, when we describe elements, and I've asked you guys to memorize certain symbols of elements from the periodic table. An element is a substance that cannot be broken down into other substances by chemical means. And it doesn't do you any good to apply physical means like heat and melting and so forth. Can't change the identity. Well, you can't even change the identity with chemical means either. Right? You cannot simplify. You cannot reduce an element into smaller substances by chemical means. So these are examples of elements, right? There's a symbol for iron, and we'll go into more detail about that, I think, in chapter 4. Yeah, chapter 4 is chemical foundations. We'll go into more detail, and that's when you need to be well on your way to memorizing symbols. That's a symbol for iron, aluminum, oxygen. Notice oxygen is diatomic. At room temperature and normal atmospheric pressure, oxygen is going to be diatomic. 2 oxygen atoms together, it's still an element, right? Because we have the same atoms bound to each other. And hydrogen is similarly diatomic. Now, the entire universe is composed of elements. How they combine with one another, that's physics and chemistry. If they combine one another to where you have 2 or more different elements, we are now describing a compound. And we know it's a compound because it can be broken down into elements by chemical means. We just did it on a couple of slides before with water. We took the water and we split the molecule into hydrogen and oxygen. Those are elements. Water is a compound of hydrogen and oxygen. but we were able to reduce it to its elements by, or decompose it, I should say, to its elements by chemical means. Right? Carbon dioxide is another example. And we're going to learn how to name these compounds eventually. I think chapter 5, we're going to learn how to name these compounds. And there's table sugar. And notice we have different elements, 2 different elements for water, 2 different elements for carbon dioxide, 3 different elements for sugar, carbon, hydrogen, and oxygen. A compound always contains atoms of different elements. If you have the same element bound to another of its neighbors, the same element, it's not a compound. It's still an element. One other thing that was discovered in about the middle of the 17th century, and it was proposed that all compounds have the same composition. That's the law of definite proportions. Definite composition, excuse me. Either way. So it doesn't matter what the source of the compound is, always has the same combination of atoms. At that time, of course, they didn't know about atoms. Right? They only knew elements, and they knew that the relative masses of the different elements in a compound were constant. Excuse me. It wasn't until the middle 19th century when the ability was developed for identifying the composition of a compound. Let's see. Okay, there's no chat. Okay. So let's see if we can identify how many of these are compounds. Well, let's see. It's very simple. Hydrogen and oxygen, that's a compound. Nitrogen and oxygen, that's a compound. Sodium, oxygen, hydrogen, that's a compound. Manganese and oxygen, compound. Hydrogen and fluorine, they're all compounds. Now, what's a pure substance? A pure substance will always have the same composition, and it can either be an element or a compound. Examples, water, carbon dioxide gas, hydrogen gas, gold. So we have examples here of compounds and elements. And a pure substance cannot be separated into different substances by physical means. What I mean by that is when we had sugar dissolved in water, physical means could separate the sugar and the water, and they're different identities, different substances. We separated them by evaporation. Okay? Other means of separating substances to prove that they're not pure would be things like chromatography, which we'll have to talk about later if you don't already know what it is. Distillation is a more refined form of the evaporative process. But that way we can separate substances by physical means. So if we've got more than one pure substance together, we can separate them, and we can continue to separate if they happen to be a complex mixture. Then the physical means is all we need to separate them into their pure substances. But a pure substance cannot be reduced any further by physical means. So I mentioned mixture. We need pure substances to be combined. Two or more pure substances, and when they mix together, they retain their chemical identities. This is a physical process of mixing pure substances. Another characteristic of a mixture is it has variable composition. That is, if we put sugar in water, it could be 1% by mass of sugar. It could be 10%. It could be 80% by mass sugar. So the composition is variable for mixtures. Yeah, wine is a mixture primarily of water and ethanol, but it has some other substances in it that are useful. Red wine, particularly one that's popular these days, is called resveratrol. But there are many other polyphenolics and unsaturated compounds. Coffee is a mixture. It's an infusion of an extract of coffee bean in water. So it has caffeine. It has other, let's see, what's the word for it? It escapes me. The compounds that turn coffee black. Um, uh, Polyphenols. Wood is also a mixture. It has cellulose, right? It has lignin, and it has various salts. Potassium nitrate is a potassium carbonate is an example. Actually, potassium carbonate might be a product of burning, so it has different salts in it, I think, than that. But it is a mixture, and the pure substances could be separated by physical means. The pure substances, like before, they could be elements, they could be compounds, or they could be a combination of the two. Now, when we describe a mixture, we can subdivide it into two different types. One is homogeneous mixture. Homo means same. So everywhere you look in a mixture, the composition, the ratio of pure substances to one another is exactly the same everywhere. They're indistinguishable compositions. Now, another name for homogeneous mixture is a solution. Now, we normally think of a solution as a solid dissolved in a liquid, like salt in water or sugar in water. But mixtures, solutions, excuse me, solutions can come in many different forms, combinations of phases. All right. Here's an example. Let's see, homogeneous mixture, air. Air is definitely a homogeneous mixture. Um, an interesting characteristic of gases is that when you mix two or more gases together, you always get a homogeneous mixture every time, without exception. And it's just think of it on the microscopic level. What does this gas need of this gas to make the mixture work? It needs space. And gases have space in abundance. So we take this gas, put it in this gas, and it's got plenty of room. And there's room in there for everybody. Brass is a homogeneous mixture. It's a solid mixture. You can't just put copper and nickel side by side and get brass. You have to melt them, mix them together. Then when they solidify, you have a homogeneous mixture. We serve table salt in water, you get a homogeneous mixture. The other possibility is a heterogeneous mixture. Hetero means other. They have distinguishable parts. In other words, the composition of the mixture in this region is different than the composition in this region. They're not uniform throughout. Good example of that is sand and water. If you mix sand and water like we've done here, what happens? Well, as long as you're stirring it, it looks homogeneous. But once you stop stirring it, the sand starts to settle. So different places in that mixture have different compositions. Oil and vinegar, right, is a heterogeneous mixture. If you make your own dressing, you take oil, put some vinegar in it. Let's just, for argument's sake, say 1-to-1 ratio. And then I like to use these little Armor jars that the chipped beef comes in. And then I just clean them up, and I put oil and vinegar, and then I take a little Mrs. Dash, throw it in there, snap the top, and just shake it like crazy. What you're doing is you're breaking up the oil particles so they're small, but it's still heterogeneous. What you try to do is open the lid and pour it on your salad before it has a chance to separate. But if you let it sit there, it will separate, oil on top, vinegar on the bottom. And in the process, as it moves, its composition is changing throughout. It is heterogeneous by definition. All right. Which of the following is homogeneous? Okay, we have these possibilities. First of all, if you're going to solve a problem by answering a question, look at the question and see what's the logical way to approach this so that we can minimize the effort. One way is to work the problem backwards. Which of the following is a homogeneous mixture? Let's look at these and see if there are any pure substances. We can eliminate those because they're not mixtures. So if we look down through here, we see that water is a pure substance, right? You can throw that one out. Let's see, mixture. Copper metal is a pure substance. Throw that one out. So now all we have to do is compare these three, gasoline, jelly beans, and soil. So how would it be homogeneous? It would have uniform composition throughout, right? Gasoline is just that. Gasoline is mostly octane, which is a hydrocarbon that is neither here nor there at the moment, but is the major component, and other things have been mixed into it. Nowadays, up to 10% ethanol is mixed in there. And then depending on the manufacturer, the company that's preparing the gasoline, they'll put some other things in there, and usually they claim that they keep your carburetors clean and so forth and so on. But it is a homogeneous mixture. All right, so we know that that one is. How about jelly beans, a jar of jelly beans? If you've ever looked at a jar of jelly beans, you see different colors, right? And you tend to see one color grouped here, one color grouped here, one color grouped here. So they're not uniform throughout. Jelly beans in a jar form a heterogeneous mixture. Soil may be a little trickier for most students, unless you're a gardener or you have someone in your family is a farmer. You may realize that if you dig down through the soil, you're going to see differences in color, first of all, differences in texture, also, as you go deeper. We call them soil horizons. So soil is heterogeneous. Gasoline is the only homogeneous mixture in this group. Now, we can separate mixtures by physical means, and it just depends on the identity of the substances contained in the mixture and how they respond to certain physical changes. So we look at their properties and we use their properties, the properties of the substances in the mixture, to separate them. So if the mixture is composed of substances that have different boiling points, for instance, corn mash, a moonshiner will separate the ethanol from corn mash by distillation, because ethanol boils at a lower temperature than water. So he heats it up, and the ethanol comes off as a vapor and condenses, and the water's left behind. That's distillation. If we have different states of matter in the mixture, or even different particle sizes, we can use filtration, right? We choose the filter with the right pore size, so that we only let the very smallest ones through, and we hold the larger ones behind. Now, differential adherence to a surface is the principle behind chromatography. Originally, I think chromatography was used whatever substance they had as a stationary, we call it the stationary phase, was paper. And we can still use that today as a quantitative measure of the composition of a mixture. But what happens is, let's see, I better draw this one. In chromatography is you have what's called a stationary phase. We're going to use a strip of paper as our example. This is the stationary phase. It stays put, doesn't move. Then we have our mixture that we place here. We could place several of them here. Same mixture. We just dot them on the paper. Then we put the paper in a container, and we put a liquid. It could be, the liquid depends on what you're trying to separate. So we just keep it generic now. It's just a liquid. And it's just here at the bottom of the paper. We don't completely submerge our samples, because if we do, they'll dissolve into the liquid and they'll be gone. We want them to stay on the paper. So what happens is, and you'll notice this if you take a piece of paper and put it in water even, the water will start wicking up the paper. That's called capillary action. And it will keep moving up the paper until the weight of the liquid is too much and the capillary action hadn't got enough force to draw it up the paper. So we help it by sealing. We seal the container. Now we get vapor from this out here also. So what happens is, as this solvent moves up, right, moves up the front like this, keeps moving up, the sample moves with it. But if it's a mixture, and one component of the mixture is very strongly attracted to the paper, then you will spend more time on the paper and lag behind. Those that prefer the mobile phase, or the liquid, will move faster. And we get, over time, we get a separation. So you may have something here, you may have something here, and something here from that one, and that separates the mixtures. That's chromatography. Chromatography means color writing. And the one of the first separations that were made was extracts of leaves, right? They have mixtures of various colored compounds, and they could be separated into their various chlorophyll, xanthophyll, carotenoids, so forth. If we're volatility, it's kind of a second cousin to boiling point distillation. If we simply want to separate something, say chat. Let's see. Yeah, no problem. Yeah. Whenever you have to go, and I'll keep recording. Um, Boiling point is more a mixture of, say, liquids that have different boiling points. Volatility is more like a mixture of something of a non-volatile substance in a volatile substance, say like sugar in water. Then we can evaporate the water, and we don't have the ability to evaporate the sugar. Besides, if we got it hot enough to evaporate, it'd probably decompose first anyway. So they're related in some fashion. We're evaporating one of the substances in the mixture. Okay. There are many other physical properties that are used to separate substances. Chromatography is a massively complex field now, right? This is a very simple description, and it generally is an umbrella for all types of separations using chromatography. Only now we can tailor the stationary phase and the mobile phases so that we can separate substances. Even you may not have heard of this term. It's called chirality. You can have a compound that's exactly the same um, composition, right? Mass composition, and it has a very similar structure, right? Connectivity, they call it. The connections of the atoms to one another are the same, except um, at least in one position, two of the atoms are flipped in their position, and it changes the nature of the compound. But in order to separate one chiral compound from its neighbor, they're so similar, you have to have a special stationary phase that is itself also chiral. Okay, so this is a diagram of a distillation apparatus. This one on the right uses simply evaporation. This one on the left uses distillation to separate mixtures of liquids. What will happen is you reach a certain temperature and the substance starts to boil off the first compound or pure substance of any kind. And the temperature will remain constant until all of that substance has moved, has gone. And that's why we have this thermometer here. We can tell when the change occurs. And that way we can fractionally distill. Well, that's not the proper term. We can fractionate by noticing the temperature. So at this temperature, we used to do this in the lab, I think as a student, separate a mixture of two or three or four volatile liquids. And when the temperature starts to go up again, that means the next substance is being evaporated. So we catch the first, and then we pull that out, put another um, tube, some container here, catch the next one. When the temperature rises, starts to rise again, catch the next one. Okay. So no chemical change has occurred when the salt water is distilled, and we use distillation to purify salt water, seawater, so that it's drinkable. Excuse me. Filtration, right? We separate a liquid from a solid, for instance. All we need is a filter of the correct pore size to retain the solid. The liquid goes on through, and now we have a separation. It's based on phases and particle size. Okay, so we've talked about matter so far. We can say matter, more than likely matter is going to be a mixture. It's either homogeneous or heterogeneous. And with physical methods, we can separate the mixtures into pure substances. Of course, if the matter is already a pure substance, then we skip this step. We're already pure substance. Once you get to pure substances, and these could be several of them, then you can take each one of those and you can convert it into elements by chemical means. Or you can well, the pure substances, if they're elements, you've already got them reduced to their ultimate smallest size. But if the pure substances are compounds, then you need a chemical method to reduce, to decompose the compound into its elements. Now, this is all chemistry. This is physics and chemistry. We're not talking about nuclear science here, because we know, and we're going to find out subsequently, that elements can be reduced further, but not by chemical means.